Okay, welcome to week 9 of Fundamentals of PLCs. This week we're gonna do some more drawings. So this week we're going to look at how to identify PLC signals on P and ID drawings. So process and instrumentation drawings, which are besides IO drawings and electrical drawings, are a very big part of any process. We're going to look at some of the most commonly used symbols on PNID drawings for representing pipes, fittings, symbols, valves, gates, actuators, pumps, a bunch of miscellaneous symbols, how to interpret some of them, how to interpret the process flow of PNIDs. Has anybody used PNIDs before? Seen them? They're really big, oil and gas, water and wastewater. There's actually governmental mandates to post PNID drawings of your entire process. Yeah, you've seen some, Addie. Yeah. They've been around for a long time. PNIDs predate PLCs. Back when most instrumentation were mechanical devices. So they're a pretty important part, especially in water and wastewater, like I said. But you'll find them in food, beverage, pharma, hydraulic and pneumatic systems will have PNIDs. You'll find them all over the place. You'll even see PNIDs if you read through your fridge manual and your freezer manual, because you'll have pumps and compressors and all of that. So they're all over the place. So PNIDs in a nutshell, they refer to process drawings, and they are used to describe the instrumentation, the control loops, and the flow within the system. So whether that be water, air, oil, gas, product. PNID stands for process and instrumentation drawings, and they visually describe the instruments in a system and their connection to each other, as well as to PLCs, interconnection between panels. They can also show. So a disclaimer here, small, large, it's one page, but these slides don't show all possible symbols. There's a number of different IEC and ANSI standards. You can get a lot of these. I can pull a bunch of the most common ones. Anyone can find these off the internet, but the most common ones are in here. But there are a lot of other ones available. So this is by no means an exhaustive list or an examples of all the symbols you may see, but we're going to understand how to read through the drawings, and then any well-engineered PNID will also have somewhere near it, there will be a legend. So some of the most common symbols: valves. So a valve at its basic form is used to stop or direct process fluid. Air, liquid may be the most common, but again, fuel, you're in a dairy, milk, anything that passes through pipes or channels. A valve is open. When a valve is open, fluid can flow through it. And when a valve is closed, fluid is stopped. You can also use a valve to throttle. So you can have discrete valves, which are you tell it to open and it will open to 100%, and tell it to close and it'll close to 100%. And then it will have a traveling state, so it's neither open nor closed. You're going to have an analog valve, or called a modulating valve, where you would use a 4 to 20 signal to tell it to open to 20%, open to 100%, close to 0%. So whether the valve is discrete or analog will typically be determined for that process during the design based on either what the valve is doing, if it's trying to stop flow completely, if it's trying to throttle flow. There are three-way valves that can be used to direct flow down multiple paths. So valves can be three-way or greater. I haven't seen more than three-way valves myself, but an example of a three-way valve would be your kitchen faucet with a single handle. The faucet would be a three-way valve. One is for hot water, the other one is for cold water, and then the water that exits the faucet itself would be the third. So there'd be a mixing valve. And then the valve you control with your hand would be mixing the right ratio of hot to cold to wash your hands or wash your dishes. Three-way valves would be a modulating valve that would work very much the same. You can get pressure actuated valves that will automatically change as well. That could be three-way valves. In Kitchener-Waterloo, if you rent a hot water tank from the city, they've put a mixing valve in your house that I believe you pay $3 a month for. So that automatically, and it's called an anti-scalding valve, but I digress. So here's some common different valve symbols that you could see. And again, this is by no means exhaustive. So the first here is a generic valve, two triangles that meet in the center, opens or closes to allow or stop flow. This next valve, bottom left, would be called a ball valve. So the ball valve is just a little more descriptive. Also would open and close to allow flow, but the inside of it actually is a ball. So depending on your application, a ball valve may be all you need to potentially throttle flow. So the pivoting ball with a hollow center allows flow to travel through, and it connects its entrance and exit there. The next one up here with the little line is called a butterfly valve. So a butterfly valve actually opens and closes. It rotates this metal disc. Kind of looks like what the symbol is. Yeah, as it closes to vertical, it just blocks more of the flow. I see these used a lot to throttle flow under high pressure. These seals tend to leak a little, so some applications may not work for this. If you have an application that might have a lot of debris in the water, it could jam a butterfly valve. So might not be the best design decision, but that's what one looks like. And this last one would be a check valve. So a check valve is just a one-way valve. So they'll only allow flow typically in the direction of the arrow. Check valves are put in to prevent either backflow from a pressure system, or even I've seen this type of slanted disc check valve would be connected to a pump. The pump would push against it, and as the pump built up enough head pressure to start moving enough water, then the check valve would slowly open. So sometimes these check valves will act as a double duty to allow your other mechanical equipment to run more efficiently. So like I said, lots of valves. that you'll see all over the place. So this is a diaphragm valve. So these can be discrete or analog. Um, Again, this is very common for larger size throttling applications. So as the actuator pushes this, you can see kind of this piece, it pushes this diaphragm through the throat of the valve. Um, and the further down it goes, the more it would throttle down the flow. Um, I see these used a lot for water flow applications, when sometimes you just can't slow a pump down enough. So this is a diaphragm valve with a hand jack. So that's really just indication, or when you see a valve with a hand, one of these T's indicates that it could also be manually opened or closed. So this is a diaphragm valve with a wheel on the top, where this one may or may not actually have a wheel. It could just have an electrical actuator, which just means it's powered by a tiny motor inside of it, maybe not tiny at all. And this one would just be hand actuated. Like I said, the T indicates hand. So this is just a hand valve. These come in all shapes and sizes. This particular one has a small handle. This is like you'd have in a garden hose. These could also show, these could be the quarter turn open and close, ball valves as well. It doesn't have to look like this handle. I've seen this used as for the ball valves. And they're not always, sometimes these symbols aren't used. They're used interchangeably and sometimes incorrectly. So just because the hand valve is shown to be a hand valve doesn't mean it's going to have this top on it. So did that make sense? Like I'm rambling. That not make sense. Perfect. This next one here is a motorized valve. So we've seen, you've probably picked up on the theme that anything with a circle with a letter in it is normally motor or control relays. So the motorized valve here would, it says typically be an analog valve. We, on the PNIDs that I see, that's true. You'd have a modulating valve for a lot of these applications. So that just means that there's a motor. So for this valve inside here, this eye sight would be a viewing port to see the status of the valve. You'd hook this up to a PLC, and there'd be a motor that would run inside a small gearbox that would then be tied to the valve to open and close it. This could be a 90, this could be a ball valve, but it doesn't really matter. This is the indication here is that we would have remote control of this device. All of the ones up to this wouldn't indicate that we would have control of it remotely. There's no electrical connections to them necessarily. This last one here is a solenoid valve. So solenoid valves are, it says typically discrete. I've never encountered a non-discrete solenoid valve. They're set up where a digital output would be used to either close or open the valve, depending on if it was a normally open or normally closed valve. The solenoid is a magnet that would then either push or pull the valve open or closed. On the inside, they could be a diaphragm valve. They could be any number of, it could be a small solenoid plug valve. But one thing to note is I have only encountered one solenoid valve that had feedback. So when using solenoid valves and finding them in the field, you typically have to send them the command to close or open and assume it's done that based on the output firing. Uh, with the motorized valve, you can typically get an open and closed status back from them or a position status, but solenoid valves, unless you have an upstream or downstream flow meter or pressure meter that you can infer opened and closed status from, you're normally working blind with those. So other common symbols used, pipes and fittings. So a pipe and a fitting is your process flow tube. So stainless steel, copper, cast iron, PVC, anything. If you're working with an air system, it could be PVC tube, whatever else tubing you would use for airflow. There'll typically be call outs for them in the drawing. So it'll indicate diameter and material for the piping. Piping can be various sizes, various diameters, and composed of different materials. An example I see a lot would be process piping, so stainless steel piping, transitioning, having chlorine injected into the system. Typically, that's going to be coming from a medical tubing that would then have an injection manifold that would be ported into the side of the stainless steel piping, and then those would be mated together. So you would have the hypochlorite being run right into the center of a pipe to make sure it's getting mixed properly. Piping can be insulated or non-insulated. That means exactly that. And then you can actively or passively insulate them. And then fittings are physically inserted into the pipe to achieve some purpose. So whether that's restrict flow, connect to a larger or smaller pipe, a drain, a blind flange, which is just dead ending it. Fittings are even mounting pipes, pumps and devices in there. So when you connect a pump to it, you're going to have some kind of flange fitting. So commonly used symbols here, we'll have insulated piping, air vacuum release. So that's a device to be mounted on the top of siphon breaks. Sorry, I'm kind of skipping around here. I'll go through the slides as they're animated. So insulated piping, useful for maintaining fluids of a specific temperature. So if you have a hot fluid and you want to keep it hot, or you don't want the heat escaping, you can wrap the piping in insulation, and then you can add additional jacketing around it to protect the insulation if this is going outside or you're in a factory setting and you don't want your fiberglass or rock solid insulation. You can also get, sorry, I hit my mic. You can also get actively heated systems called heat tracing, where you can wrap your pipe in essentially a heat coil. It's like a wire, and then you put insulation around it, and then you run current through it, and it heats up like an electric heating blanket. That's used in water systems all the time to keep the pipes from freezing. People will do that for downspouts and that in their house to keep it from freezing and damaging foundations or weeping systems. Here we have air vacuum release. So it releases pockets of air that collect at high points and can also release vacuums. I've also heard them called siphon breaks. Siphon breaks typically are something that they act a similar way, but you would manually, or at least you would act upon it to break the siphon if you wanted to stop flow. This is an example of a plug, which is exactly that. It's just a rubber seal, or some call it a bung, to stick into a pipe. Yeah, it's just the triangle into your process piping. So for all of these, you can see here, the main black line, that's your piping, whatever your media is traveling through. This is indicating it's insulated. This is a plug into the end of it. Here, there would be a line, and this would be coming off of it to indicate a vacuum release. Gates. So gates and valves, they do similar things, but they're not exact. They're a little different, because valves are typically mounted on piping, where gates would be mounted on open channels. So here we have an example of a sluice gate to the left, where this one is that gate open and this one's closed. So it doesn't look like a drastic change, but it has slid down to prevent the water from moving underneath it. But as you can see, if the level comes up high enough, gates will allow water to come over the top sluice. Slide gates. So slide gates are movable gates that can allow fluid to flow when moved. They typically slide left and right, so side to side, where this sluice gate is moving up and down. Butterfly gates have butterfly latches to make them easier to operate than a standard gate. Butterfly gate will swing open. The reason why it says that they're easier to operate is if you have a lot of water sitting on one side of a gate and there's no water on the other, there's a lot of pressure on it. So if there's a whole bunch of water pushing against this closed gate, it's pushing into this frame, and you have to overcome all of the friction plus the weight of the water. So a butterfly gate, half of your pressure on your gate is helping you open. It's supposed to be easier, but there's still a pain in the butt to open. Sluice gates are movable gates that allow fluid to flow underneath them when raised, and when lowered, like you can see here on the left, they would stop. But typically they're designed that the top of the gate would be below some overflow level to prevent overflowing some process that's still downstream or upstream of this gate. And then flap gates are the check valve of gates. So they're typically hinged. You normally don't control them. They will flow in one direction and not the other. These would be used if you had they're used a lot in sewage systems. So if you have a heavy rainfall and your sewage tank in the ground fills up and overflows, it'll overflow into a rain. They're called I can't think of the acronym right now, but they're used as overflow gates, CSO, combined sewage and overflow. And as the water overflows into the other gate, a flap gate at the bottom will allow that water to travel back into the main wet well as the rain event's finished. But as the water is no longer on the overflow side of it, that flap gate will close, and then the sewage can't flow through that gate. Does that make sense? Does that not make sense? It's not that important. It's just the only example I have of one. So as we talked before, we'll have process symbols, and then there are accoutrements that can be added to these symbols. So modifiers for them. If I say pilot lines, does anybody not know what a pilot line would be? So this pressure control valve here and this pressure control valve here, these lines on the outside of them are called pilot lines. So this, the external one, let's say this side is pressure regulated to open and close based on a system pressure. This pilot line will be connected to the control pressure and then run into the diaphragm. So as the pressure goes up or down on this side, it would act upon the diaphragm plunger to open or close the valve. So you can use the system pressure as a surge protection, for example. So the pilot lines, whether they're for valves, pump control, pilot switches, they're just a pilot line running to a specific spot is just kind of your control for that device, but not like a PLC control. These would be like a hard physical control for those devices. So here we have a pressure regulating valve with an internal pilot. So the valve controls the pressure to a desired value and feedback is received from that internal pilot. So it's set somewhere in here, there'll be a regulator that is set to 30 PSI. And the 30 PSI is measured, and this is calibrated that this valve is holding 30 PSI in one of the areas inside this valve. It's hard to tell which one specifically, but this is a diaphragm valve. And one of the things to note is this valve could be the size of a water glass, or could be, I don't know, the size of a Volkswagen Beetle. These PNIDs are not necessarily representative of physical size, just process representative. So this would be an example of a multi-port valve. So it might look like this is a square, but it's actually it's 3 triangles. So remember, we've got the 2 triangles here for a valve. Here we've got a third one to show that you could have multiple paths of water, but the arrows show flow. So for this valve, we have one process line that feeds 2 possible outputs, where if we had an arrow coming here and an arrow coming here, and this indicating that they both go this way, then this would be acting as a 2 input, 1 output mixing valve. Does that make sense? So this valve is able to send fluids in 2 directions or receive fluids from 2 sources, all depending on indications in the drawings to interpret the flow, the path of the fluid. So here's a pressure regulator valve with an external pilot. So again, just like this pressure regulated valve, there will be some either a needle valve or something in here, a pressure gauge to set this to, and this valve will move based on the pressure off the pilot line. This is a pressure relief valve. So useful in storm conditions when water increases and pressure needs to be released. These are found in a lot of places, especially if you have steam or heat. A buildup of pressure can come off. I think you've got a couple of them on your water heater if you've got a boiler tank. Well, you'll have them on a inline too. Any questions? gonna try to get through these quick. So some miscellaneous symbols here show a drain. So kind of like ground, it shows there's normally going to be a break between your normal process line to show a drain. You never want to show process line connected to a drain, because then the drain could potentially connect to your process. Nobody wants to drink sewage. So useful for dumping excess water, product into a vat. Normally just show an air break. This would be a pipe reducer. So it does exactly that. It's for connecting pipes to different sizes. So it reduced down, I believe you flare up. They're the same part. In theory, you just are going from small to low, or low to start, big to small, or small to big. This is a filter. So useful for removing particles. So you'll see filters in water systems, air systems. Air systems, you'll normally see filters, and then you'll see a drain line for collecting and drying the air to make sure that you don't get moist air inside your very expensive air valves. Any of you guys who have worked in assembly lines, you've probably seen these all the time. And then this is a flange. So flanges are used to connect different pieces of pipes to one another. There'll be flanges on pumps, flanges on instruments. So depending on the size of the pipe, the size of the flange may change. A blind flange, so this would indicate here is actually a blind flange where two pieces of pipe would meet with nothing in the center. Flanges are really just the connection points between anything. If the pipe needs to bend, if you're putting in elbows or 90s, flanges everywhere. And the size of flange is dependent on the pipe and that application. Okay, so now we're getting into some of the PLC portion of this. So some general symbol notation that you're going to find with some of these instruments and valves. So instruments, computers, displays, and PLCs will typically all use different types of squares to represent what they are. So we've got discrete instruments here as circles, shared instruments here in a square. So if there's a device that's wired to a PLC only, or a device that's wired to a PLC and maybe hardwired to some system, it's showing up here as a square. A computer function within a hexagon, and PLC logic outputs, inputs as a square with a diamond in it. This is an example of what I see commonly, but I've seen other shapes. I've seen some drawing sets only have one shape. And you can connect discrete instruments and PLC logic together. So you can see these things chain inside a drawing set. And I will show you a bunch of examples. I'll try not to go overboard like last time. Just trying to show lots of examples, unless you want that. So instrumentation symbols that we'll see. So when you're looking at a P&ID, process and instrumentation drawing, you'll have your devices and your process at the bottom, typically the bottom to the middle, and then all the signals will connect up to the top. And you're going to see somewhere it's going to say DI here, DI, AO, AI, AI, indicating the type of input to your PLC. So signals will usually have an indication as to what they are. The instrumentation symbol will indicate that the device is connected to a PLC and will often indicate which PLC. So down here, we have your PLC. So your PLC, your logic, and in this instance, it's PLC 112. Sometimes there's leading lines to indicate instrumentation. So you can see, sorry, I want to, so here, again, if you look, this line with the circles on it, may be indicating hardwired. So again, you have to know what's going on inside the specific drawings that you have and see if these wires mean anything. So this looks like it's indicating hardwired, and you have an arrow going into the PLC, and now we have a hardwired AO coming out of the PLC. In the next slide, if you pay attention here from the AO, sometimes lines leading to instrumentation will have MB or PB or other abbreviations, and the line type here could also change, which would be described. These would be described in the drawing set. These abbreviations are commonly Modbus or Profibus. So those are, has anybody heard of Modbus and Profibus? I mean, not heard of them. Anybody worked with them? So Modbus and Profibus are what are called field bus protocols. So they are they're not they would be a network connection. So if you had a Modbus output, that would indicate to me that this line, even though it's the same as these ones, would be Ethernet or a serial connection or a Modbus signal from our device to the other device, which means that it wouldn't be a hardwired analog output. Profibus is just Siemens. If anybody's ever heard of that company, Siemens, they also make PLCs, and Profibus is their proprietary field bus protocol. Instrumentation symbols continued. So you can see here in this example, we have an instrumentation, a field mounted piece of instrumentation. That's going to be these temperature sensors. They're out again, typically field mounted. So we've got a pump coming out of the pump. We've got some pressure and temperature sensors. We've got our process line coming into the pump and a process line leaving the pump. 500 would indicate the diameter, and PW and SS would indicate material of that pipe. Okay. So these are mounted in the field, and then there will be somehow they will be connected up. If they're connected to a PLC, there'll be a line coming up to the top to the PLC signal here. PLC signal typically has the instrument tag inside of it. In some level, this may be, if you remember back to tags, we had multiple tag fragments. So SI may be the final speed indication, pressure indication, flow indication, speed set point. So some indications of what the tag is, and then 11210 may be the specific device number, or this could be indicating the PLC. Remember, we saw this going to the PLC 112. So some sort of identifying feature of where these are going to be connected to. And then this is an example of a pilot light. So very similar to what you would find in an electrical drawing. You will typically find PNIDs inside electrical drawing sets or very close to them. So they do share some of the same symbols. So here is an example of a, sorry, my daughter's coming up to say goodnight. Give me 1 second. That was quick. Yeah. So here's an example of a process drawing. So we can see here, we've got a line coming in from the left. From this, typically this X would indicate where in the process it might be coming from, but this is saying Juno booster station. I think there's some animation here. Here we go. Okay, so we'll assume that HV 1122.0 is closed and HV 1121.0. So that is HV 11. What? Hand valve 1122. Oh, this one. So process flow comes in here from Juno station, comes down, and then because we're assuming that the valve 1121.0 is open and 1122.0 is closed, water will come down, hit the valve, and stop and flow down here through the pump. To say it comes from Juno might be, depending on how the flow is set up, might be not, it could be drawn from the pump. Depends on what the pressure is in the system. But then the process flows through the pump. It'll be through this check valve, through this manual valve. You can see here, this manual valve connects up to a valve 1A junction box. Here there is a pump junction box and a pump 1 local control panel that has some hand switches that say jog and e-stop. So by looking quickly here, you can get an understanding of, okay, well, out at the pump, we have some pressure sensors. We've got a pressure 500 mils. We can get a rough idea on how big the piping is coming out of that. So that's 0.5 meter. Typically that would be the inside diameter, I believe. But there will be, you could have schedule something, different schedules. You can see here 600 mils is what comes in. It gets reduced down as the water flows through the check valve, through this motorized valve, comes out to the end, branches down. It will actually leave out to Juno booster station. I don't understand how it's coming and going from Juno, but let's just ignore that for now. The water will actually, or the process fluid will come down here, come back, hit the check valve and stop, and then continue on to Azkaban booster station, Abzan, after traveling through this valve chamber. Does that make sense? How to read that process flow? What about this backflow? What about this backflow? So this backflow will hit, again, the check valve because it only allows water to flow in this direction. Make sense? Or any questions? I'm going to throw up a couple of examples of PNID drawings from my the bunch that I gave to you guys, and then I'm hoping, what time is it? Another half an hour or so, and then you guys can get going with your assignment for the week. So in conclusion, so process symbols can either be device symbols or symbols for signals. PNIDs are useful for showing all the devices connected to a PLC, but as well as visualizing the actual process flow. So valves are useful for allowing or preventing flow. Gates are also useful, but they're used in different applications. And we have pumps. I don't know why pumps weren't listed, but there's also pumps. Do all PNIDs have PLCs? No, they do not. So process and instrumentation drawings have existed before PLCs. I've seen PNIDs from the 70s. It's all you don't need a PLC to have a process. All right, so here's the region of Cantor PNID. Kind of goes along with the reading material for this week. You guys read through it and then do the quiz. There's no assignment this week. I misspoke there. There is a quiz though. So you can see, am I still sharing? You guys can still see this?
No.
No. Dang it. Closed my thing. And now, what's going on? You are sharing. Yeah. So this is that same drawing from the presentation. So you can see how this is broken out to indicate field, MCC. So that's your motor control center. You got your PLC panels, and then you've got, this says SCADA. So this is supervisory control and data acquisition. So this is very typical to the way I have seen all of the not all of them, but most of the PNID drawings that I've worked with. So you've got your main water process. So Juno station, for this example, water would flow in here. Booster station is a water term. So this is a 2-pump booster station that's going to take water from Juno station. It looks like boost it back to a different Juno station and further away. So you can see here, some of the things that I'd look at very quickly are, we have, again, 2 pumps, and then you can trace up here, pump 1, pump 2. You see these lines that leave the pump, they come up. This indicates here we've got pump 1 wired back into pump 1 junction box. The dashing on this is a little big. I don't like the line scale here, but these sensors, these instruments are also wired back into pump 1 junction box. And it does, and then here we've got the valve, and then the valve open and closed. So the open and closed sensors are wired back to the valve junction box. These then feed up to the MCC. So inside the motor control center, which I showed you guys a photo of. Does everybody know what I mean by motor control center? You might not know what I mean. It's going to be where the VFD may live, the main motor circuitry, high voltage, higher voltage, technically medium voltage stuff. And then from the MCC, we have a connection back to PLC 112. This particular PNID only has one PLC 112. Normally, when you only have one PLC, you don't say 112 on all of them. You would just say PLC. But you can see here that pump one, this is all of the IO that you would expect to be wired back to your PLC. So we've got an in remote, a running indication, a fault, a run command, a temperature high alarm, a pump discharge valve open command, a pump discharge valo, that's a typo, valve closed status, an discharge valve open status, a speed set point, a flow indication, a pressure indication, and a speed indication. And we have pump two, and you can see quickly that it's the same IO, which is good for programming. So we have two pumps with discharge valves that need to open in concert with one another. Whether that means that you start the pump first before cracking the valve to build up back pressure, or you have to open the valve to a certain percentage. That information we can't get that type of process information, but we do know that this valve would have to be open before flow could pass through here. So when we look back here at valve 1A junction box, there's an error there. Valve 1A and valve 1A should not be able to exist in two different spots in the same drawing. If they did exist in the same spot, they'd have to be shown that the wires came to the same spot. So there's an issue with that. If you caught that, good eye. Then you see here for this valve, we have an open and closed status. We have another open and closed status that comes down to the other valve. And here is a surge relief valve. So it goes all the way down to a surge setup. So these valves, again, this is showing these are surge relief valves, but not familiar with exactly what type of valve that would be. It kind of looks like a ball valve, but that is not the type of valve I typically see for surge. Surge relief would normally, there would be a controller set up around here. So they would kind of monitor pressure. And if a spike in pressure were sensed, these valves would open and then dump additional water to a drain to prevent damaging any of the equipment in here. So we have here a flow meter. So one of the things I don't love about this is it's not showing where the flow meter is. So we see we've got pumps, we've got reducers here. So we have a line coming in and a connection, 600 meters flow in this direction, 500 millimeters. So we do have a change in pipe diameter and then potentially another change in pipe diameter, but it doesn't indicate what it is. We move further down past the two valves. We see some hand valves. These would be up pointed valves either for taking sample points. Potentially these could be future injection points, or they could be air brakes, vacuum brakes, just drawn incorrectly. What these drawings won't show is if there's an elevation change to try to keep sections of pipe higher or lower than other sections of pipe. We do have a drain here that would indicate this is a low section of the piping system. Here we have a flow meter. So here's one of the flow meters, FM 1125. We can follow that up to PLC 112, and we see that we have a valve chamber forward flow, a valve chamber reverse flow, and a flow meter fault. We have motorized butterfly valve that has a reducer and a flare on either side of it. So it looks like it's stepping up to a meter in diameter pipe. That is a monster from, I don't know exactly what this side is. What else we got here? Flood chamber, so that'd be a float. So this is a valve chamber float. And that looks like they've drawn a sump pump. So if the valve chamber were to flood, there's a sump to pump it out and the sump pump fault. So there's a lot of information on these. This one's not bad. But does it make sense how to read these? You're typically, I want to say typically you're going to read from left to right, but depending on who's drawing it and how the process actually flows, that could go out the window pretty fast. You can get a lot of ones where you can get these flow, these connections stating where you need to go, and you can get lost in them pretty quick. Any questions before I start opening some more drawings? The relief valves in the left. These ones?
Yeah.
So the way I read this is the surge, there's actually going to be some sort of drain or possibly upturned, like this could be atmosphere. So I'm not seeing, I would have expected for surge, I would have expected to see like, I lost my drawing thingy. Sorry, I'm just pulling up my pen. I would expect to see like a pilot line like this. Typically they'll like monitor each other's line, something like that. So it'll be able to sense, okay, I'm opening, so I'll throttle one open and close slowly because this is an open, normally open and normally closed. So they'll kind of like modulate back and forth to slowly allow a buildup of pressure through to prevent something in here from exploding. Because if we're looking at this, so 100 or 1,000 millimeters, so 1 meter in diameter, that is a big line. So these I'm guessing it's not in here anywhere, but I'm guessing these are going to be like 800. Yeah, there's 800
This is 600.
in here.
Yeah, left side, the dark arrows.
These ones. Yeah, that's these pipes coming into the pumps, and then the outlet of the pumps is 500, and then it steps up here, and so it goes down and then up, it goes down and then up. So this is between 500 and 800. So these, like, for surge protection to work, you need to have some sort of pressure monitoring, And because there's only a DI coming out of these, because you can see that based on what we have up here, the PLC only knows that the surge valve has opened to prevent a surge. But like in this case, it looks kind of like a surge protector on your I don't know, your TV system or your audio system or your computers. It might tell you that there was a surge, but we might not know how it did it or when it happened. So this is a case where I would look at this and I would ask the question or try to find more mechanical drawings to be very like specifically how this is going to be assembled. Again, we have the PNIDs are a fine line between explaining how your process is going to function and having too much information. So if we were to show, if you were to try to show this valve, for example, if it's a Singer diaphragm valve from of that size, there's probably 4 or 5 different solenoid valves to make sure it moves, and like 8 for every solenoid valve. So there's 4 of them. There's going to be 2 needle valves on either side of them so that you can calibrate the solenoid valves, plus a few drains and a bunch of pilot lines for safety. You can't, that's not really sustainable on a drawing that would be at this kind of level of granularity for what we need. Does that make sense?
Yeah.
I like that's my long way of saying I don't know, I guess. But somewhere else on the drawing set, you should be able to find the information, the detailed piping diagram for how the surge will relieve pressure. And I might have an example of one of those I could show you today. Sorry, I moved my example drawings. Let's see if I can find. Sorry, the PNIDs should be here. So this is like 75% design for a station that is currently under construction in Guelph. And you can see stylistically, this is the PNID, but there's a lot more going on at this station. So where is so we have inlet flow here from zone 1 and inlet south, and inlet here from zone 2, the north inlet. So the city of Guelph is broken into a number of different pressure zones. So this is a booster station that will take water from zone 1 and then we'll boost it, add pressure to it into zone 2 to fill one of the towers in zone 2. So we've got flow coming in here. There's a valve in the street. It's actually indicating that we're coming up through the floor into 400 mil pipe. And now, because there's so much stuff on this drawing, you can see that we're using these squigglies again. So we've got butterfly valve 1 and butterfly valve 2. So if you remember from some of the other drawings we're looking at, we've got a butterfly valve, we move up, and we need to find where 1 and 2 go because these squigglies indicate that there's a disconnect. So if we move up here, we can see MCC and local control panels, that's everything in this section. So this is the field. And now we've got PLC. So Paisley PLC number 1. That's the only PLC there. So everything that's wired to a PLC goes to that one. And then this is SCADA pulling the descriptions. And because this is only 75% design, we hadn't had a chance to fill in some of these blocks with data tags. So the 100% or the as-built drawings will have the DI/DO. We have the DI/DO, but we'll have the remote status tags all up in here, the device tags that will get filled in later. So we can see here that 1 and 2, these bubbles come up and line up with 1 and 2. And if you look here at motorized inlet and outlet valves, typical 3, we can see that all of the motorized valves have the same IO. So to save on space, you can group devices that have the same IO together. These valves have a remote status, a fully open, a fully closed, a fault, a position feedback, and an open and closed command. 1, 2, and 3, well, we know these are called inlet and outlet valves. And we found 1 and 2, and the third one, if we follow the process through, the outlet would be here, number 3. Would you rather me follow the process first or go through some IO stuff? I'll speak at once. So the process, we'll do that. So the flow will come in from zone 1. We're going through here, AIT. So AIT this is a chlorine analyzer. We will find IO for that up at 22, which is somewhere 22 here, and we'll have a free chlorine analyzer. Move further down, we have temperature probe, pressure, and we can see here that there's a line that comes off. 50 mil line comes off into the temperature probe. We've got our span of it, 0 to 50. We've got a reducer. Not 100% sure what that is. I believe it's just a valve, a pressure transmitter, and then this is just a pressure gauge. So the transmitter comes to the PLC, and then there's a gauge beside it to confirm that the transmitter is working or is accurate. As we move down, there's a flow that'll run into the reservoir. So we have a flow meter, and then we have a surge diaphragm valve with a hand crank on it to kind of limit the flow so we don't overfill the reservoir or fill the reservoir too quickly. South and north, south lines and a wet well fill line. And the other inlet that comes in does the same thing: chlorine, temperature, pressure, flow into the other reservoir. And then the water that doesn't get diverted into that reservoir will come here. We have a flow meter to come on either side to come into the booster station. The water will flow down. We have air release here as the pipe actually dips up or curves up, moves down into this header. We have a pressure gauge ahead of 3 of our inline horizontal pumps. So these are booster pumps that other horizontal booster pumps. They're mounted to skids on the floor, and water comes in one side of the pump and discharges out the other side to boost pressure. One of these is running 24 hours a day. Here's a pressure transmitter on the outside of each one of the pumps. We've got 2 hand valves for isolation. If we ever need to do maintenance on the pump, we close this valve, we close that valve. We can drain the water from here, open up one of these, it spills onto the floor, we can do maintenance on the pump. The discharge of the pump runs into this header. In the future, we would discharge into another line. It doesn't exist yet, but so now it moves up, excuse me, to a flange, which then connects the hand valve. You can see here that there's a check valve right there. So this check valve will allow us to route water directly from zone 1 around the booster into zone 2 by using the pressure from the upstream pumps. So if we couldn't run the pumps at this station to boost pressure, we could turn on all the pumps in zone 1 and force water through this station through the check valve, but we never want water to leave zone 2 into zone 1. So that check valve will prevent that from ever happening. The water from these booster pumps will travel up here, won't really travel down here because each one of these pumps will have check valves, so we can't flow that way. We're going to leave through the zone 2 outlet. We could also pressure relief. So here is an example of a surge system, Vincent, that would have a diaphragm surge valve. So you can see here that as the water comes in, these are going to be set at a specific flow or a specific pressure. And then as that pressure increases on this side of the internal globe of these valves, it's going to drive the valve open so that the water will then bleed through and then pressure relief into one of the south wet well. So the south wet well is just a massive reservoir underground. So then the water that leaves the station, again, checked for chlorine, temperature, pressure. The other pumps we have at this facility, so there's, since the water's coming in, whoops, sorry, I didn't mean to switch drawings there. So the water that comes in and fills the reservoir, we boost the water that's coming from zone 1. But if we need more water, we have what are called vertical turbine pumps. So these pumps are mounted vertically in the building, and they have a shaft that runs down into the reservoirs, and then we'll draw water out of the reservoirs, and we can push that water into the zone. So at night, when usage is low, we'll pump and we'll fill the reservoir so that in the morning we can use the water from zone 1, but also add the water we've stored overnight into that zone. So that's the main water flow process. Up here, there's also a well on site. So we can draw from the well groundwater. It comes into a contact chamber. This contact chamber, this HC line here, it stands for sodium hypochlorite. So if we look HC, look for the HC discharge. We have HC, HD, and HE here. So there's different hypo pumps. You can actually see there was a H. Where was that other HD? HB, HA, and there should be another one somewhere. HD here. So these hypo pumps, they draw sodium hypochlorite that's in a 12% solution from a tank, draw it out, and then pump it into different sections, different injection points to make sure that the water is clean and safe to drink. Here, HC's put in, so hypo's put in at the beginning of this contact chamber. This contact chamber is just there to allow the chlorine time for it to mix with the water, make sure that there's it's properly disinfected. It then runs into the reservoir where it will mix with the rest of the water from zone 1, which is already chlorinated, which we've confirmed since it's been coming in. We're constantly measuring it. If there is an overflow, it overflows into the storm sewer because you can't put chlorinated water into the river or a creek. We have sample pumps from the reservoir that constantly run, pulling up water that we're measuring the chlorine still. Notice there's a lot of emphasis on chlorine measurement. Level transmitters here for the reservoirs. We're showing there's valves all over the place. You'll see a lot of generic valves. These valves don't have outdoor hand wheels. They actually have a giant, I think it's a 10-foot long T handle that turn them. And they are big valves. I think they're 700 or 800 mil. So they take 2 people to turn 450 mil. So you can guess how big these pipes are, I guess. Maybe you can. Any questions?
Hey, Brian, just
Yeah.
a quick question, just curious. Unlike pump number 2, some of the lines have a kind of like a half circle and a call out of a number like 250.
Yeah.
What
diameter.
Oh, it's pipe diameter? Okay.
Yeah. Pipe diameter. So you can see here 250, 450, 450, 350. Pipe diameter is determined based on the required flow that you need. And fluid, like the engineers determine how much flow we need and they plug it into a schedule calculator and it gives us the pipe schedule that we need for the different sections. So you don't want to go too small, but you don't want to buy a kilometer of stainless steel pipe 5 times bigger than you need. It costs a lot of money. Any other questions? Good question. What else we have here for P&ID? So here's some more process. So here's an example of a P&ID with no PLC. So this is the domestic cold water. So we bring cold water into the building, which is metered, but we don't monitor any of it for the PLC because the water comes in. We got a 50 mil line, comes through our backflow preventer. This is just a tap. So that's just a hose bib, normally open valve. There's some insulation here. We run into a hot water tank. Here's that anti-scalding valve that mixes down. This runs over into the chlorine room. We've got a pressure gauge to make sure we don't overpressure the eye wash station so we don't remove people's eyeballs. And the hot water tank is set. This is temperature set so that it's not scalding, but it's also not too cold. Here is a outside drain. So it runs through a floor drain and drains outside. We also have cold water comes over to the bathroom. So another small hot water tank on the other side of the building, toilet, sink. Here's this is kind of a single line drawing, not really processed, but again, you can see it doesn't have to be water. You can read a single line drawing like a P&ID. It's electricity traveling through wires. So it'd be the same thing. You got power coming in. here's a transformer, here's the voltage. So here's the, I don't know, pressure. You could call out here, you could call out the sizes of the wires, the number of conductors, hydrometer, ground faults, heaters, all your different devices, and anything that we have here. So we've got a 1 and a 2. I don't know where those are going. I didn't really expect to see a connection to a 1 and a 2. This is my life. Constantly looking around drawings. It says HOA to HMI. I'm not sure where these 1 and 2 go. Again, this was a 75% drawing set. I wasn't allowed to show you the 4 construction set. So there are problems. PNID drawing here for how to set up the sample pump. This one's kind of funny. It's fun. So there's a sample pump and it's showing that it's actually plugged into an outlet. So there's a cord, 120 volt. There's a hose. It connects to a flange. This runs up into a normally closed valve that then runs into a bucket. There's literally a bucket. And this sample pump will open that up and we'll use this sample line to pour into our testing beakers and everything drips into a bucket. We've got a needle valve here to bleed this line. This goes to drain. This is constantly running. This poly runs up into a 2 filter system. There's another drain, which is constantly running. Here's a flow calibration to make sure that we're only running between the proper 0 to 80 liters per hour that our chlorine analyzer can reliably run at and give us accurate readings. And in the event that the filters back up, there's a bypass. If we have to change the filters, we have to constantly be doing chlorine analyzer readings. So if we have to change the filters, we have to bypass that first, then close these valves, take the filters out, put the filters back in, fill the filters back up, and then close the bypass valve. We don't want to run into the chlorine analyzer all the time because we'll gum up the sensors with hard water. Drawings, more drawings. I might sound like I'm belaboring the point, but drawings and specs are where you're going to get all your PLC information from, and manuals. Let's see another PNID generic loop. Excuse me. And I'll let you go. You guys still see that? Yeah. All right, so, oh goodness, what have I done? That is special. Oh, that's why I'm on page 31. All right, so legend here. So sometimes they won't call out where is it? Pipe. I haven't looked at this drawing set in a while. But you can see here where they might not say AI. So an AI here is a dark black triangle, upward pointing, output is downward, discrete, and input and output. They'll be cute and they'll say they're going to use all these funny, awesome symbols, and then not use them or use them at their discretion. Here for the line legend, sometimes you'll see some of them change line weights and say that a line weight of 10 would be a specific type of piping. That only works if you have all of their line weights. And if you know CAD, you know what I'm talking about. And if you don't, I'm jealous. This PNID drawing is all right. That's too bad. This is a really big wastewater plant. And that would have been nice. I wonder if sorry, no, it's not in there. So you can see here that they actually have multiple. So this is an example of this is multiple medias coming through into this section of this PNID. So you can see that these triangles are indicating a drawing number and potentially a quadrant as to where to find this information. It's coming into 25 mil hypo PVC. This is screened and degraded gross stuff in an open channel. And then this is return activated sludge in 150 mil lines from the ROS panel. So you can see that they're separating the different medias, and you've got to follow these lines down. So we've got hypo and the return sludge all being pumped, delivered into this ROS splitter box. These would be weirs. So a weir, how do you explain a weir? So if you have water that you want it to flow into certain areas, you would use a weir and set a very specific height. So you would know that at 1 meter from the bottom of this V-notched weir is going to allow flow into these different sections of this splitter box. So that in theory, as the level comes up, it's going to evenly flow out all of these weirs, unless you want to adjust. So the weirs would be slightly adjustable, where you could pull the weir on one side up a couple of centimeters to force flow to the other side more than another. Does that make sense? So in this case, you can see the process breakdown, but you don't know exactly how this weir is installed. You'd have to go to the mechanical or structural set or portion of this drawing to see how these are installed. These could just be fixed weirs, or they could be adjustable. Here you can see that there's a motorized aeration. So this is MG. So this is maybe a gate, or maybe it's an air valve. Here we have this is a aeration dissolved oxygen sensor. So it's actually measuring the dissolved oxygen inside the tanks. These are giant. So here is a giant air diffuser, actually. So this is processed air. So here we have air from the aeration blowers. So again, these lines could be any media, and wastewater is a really good example of multiple medias. So there's air being blown down these pipes. The air comes down. Here's a mass air flow meter. It hits these and then blows down these tiny bubblers. So like imagine a straw with thousands of little holes in it, and then bubbles, like just billions of bubbles constantly bubbling up from these tanks that are the size of, this would be bigger than a Olympic sized swimming pool times 2, and bubbling like the fizziest Coke you've seen, like soda, nonstop. And so the air that's pushed in there feeds the bacteria, so you can follow the flow through. And the dotted lines are future connections. See what else we can see in this drawing set. Unfortunately, not much. I apologize. Here we have the return activated sludge pumps. So you can see that there's lines here. So the process flow, again, you know how I said I'd like to say they read left to right. Well, this one kind of goes left to right and then up. So it really depends on how the process is laid out, how to follow these lines. So you really need to watch for the process arrows. So you can see that this is a sludge line from clarifier 2. This is one from clarifier 1. So the sludge line is here. These return activated sludge pumps will then draw sludge up through, push through these check valves, flow meters, and then they'll push them out here to the ROS splitter box, which is what we saw before. So we can see that this drawing, these pumps would then feed into, and then to trace those lines, you have to jump back to this drawing. Does that make sense? How these drawings will feed into one another, and might not be one drawing into the next. You might have to go back 10 drawings sometimes to get the different information, but they're all very similar. So we'll have a pump. We've got our connections. So we'll flare out, reduce down, pressure transmitter. There's a valve. There's a valve. There's a flow meter. The flow meter, oh, sorry about that. The flow meter moves up here to, we can see that it's going into, it skips the MCC panel in this example and goes right into the PLC. And we have a flow indication, and it says typical B. So there's a style guide, a style here. So typical B means that any flow meter we now see with typical B, we know that it only has a flow indication. So if we find any other typical B, then we know there's just one flow indication and no other signals for that device on this drawing. Again, it's to clean up having duplicate information on a drawing. Here we've got, again, typical A. So we can see here that this waste activated sludge pump comes up. The wires run into this. So this will indicate that there's like a junction. So now we've got a local control station that has wires coming into it, and then it comes up into the VFD panel that's mounted in the MCC. So there's multiple connections that come up here. So this means that there's some sort of interlock that will do something. There's not enough information here to know exactly what the interlock is. Hint, hint, it's an e-stop. But when you see one of these diamonds with an eye, it typically indicates that there's something in here that will interlock or prevent this equipment from running. So if your pump's not running and you can't figure out why, and you see a bunch of things running into one of these diamonds, typically means there's an interlock that's going to prevent it. You can see the MCC is going to have a start, a stop, and a local remote switch. There's a VFD that's going to have speed feedback and speed set point. The HMI is just the interface for that VFD. And then here are some lights, alarm and run. Filter panels. So again, level, floats, high level, low level floats. Pump runs into a drain. There's a backwash pump with a motor attached to it. We can, all of this runs up into a control panel. And then you can see here, this says Ethernet. So this connection back to SCADA is not hardwired. So there's an Ethernet connection back to another PLC. So you need to watch for that. Sometimes you might have Modbus, you might have TCP/IP Modbus, RTU Modbus, Ethernet IP, CIP protocol, any number of things. They can throw curveballs at you on these PNIDs. Any questions? I could go through a lot more, but I want to give you guys time to get through the reading material, do the quiz if you want. So if there's no questions, that's pretty much all I've got. I'm going to take a 5-minute break, come back and start looking at your assignments, and let you guys do your thing. So unless anybody has questions before I go. Beautiful. I will be back in like 5-ish minutes. Those of you who survive. Oh, okay.
Sorry, the quiz is due next week, right?
Yeah. You can work on it today.
Oh, okay.
You can do it during the week. You can do it whenever you got time. So I don't know if any of you guys have seen them. There have been some anonymous quizzes kind of scattered throughout some of the week's work. One of the feedbacks that I got was that I talk, not that I talk too much. It's just that it would be appreciated to have more in-class time to do some of the work. So I made an effort to be done talking with an hour left. So if you want to do work, go for it. If you want to hang out and chat, we can do that. I just need to go to the bathroom. And then work on the quiz, go through the reading material. The world is your oyster. I wish I stopped recording before I said that. All right, I'll be back in a few minutes.